Good evening everyone, thank you for joining me on this video, the Fundamental Theorem of Calculus. I am Mr. Ish. Today is a great day because we are talking about one of the most important developments in the study of calculus, which is this Fundamental Theorem of Calculus. When this specific theorem is presented in textbooks, it's usually done in a very complicated manner in my opinion. Therefore, you end up reading through it and you get some archaic examples and it's not really explained very well. You have so much conceptual and theoretical examples provided in the explanation of this theorem that you end up losing the point. This fundamental theorem of calculus, which can be abbreviated as FTOC, is great because it bridges the two fields of calculus. You have the differential calculus and you have the integral calculus. It is a bridge between these two. You have this FTOC in between. The fundamental theorem of calculus, it just basically bridges both of these big two parts or subsets of the field of calculus. Why is it such a big deal? It's because of this. If you look at it in a very simple and basic form, this fundamental theorem calculus is basically like a coin. Think of a coin, like a money in terms of that, a coin. If you have a coin, you have two sides. You have a face and you have a tail. If one of these sides represents the head or the tail, the other represents the exact opposite. So what does the fundamental theorem of calculus say? It just says that basically both of these operations are inverses of one another. That's in the most simplest form. If you're doing one procedure on a function, the other will undo that procedure. If you're taking an integral of a function, the derivative will undo the integral effect. If you're doing a derivative on a function, if you do the integral on that result, you will undo it. So in essential speech over here, we're saying that because both of these operations are inverses of one another, you can carry out one of these operations and then undo it by means of carrying out the other. If graphically you have a function which looks something like this, and this function has the formula or the equation f of x, and you know there's an interval over here, we can represent this as a definite integral. You know that from lower limit to upper limit, f of x dx. The best way to understand the fundamental theorem of calculus is normally, in terms of examples, is by means of indefinite integrals. You know what indefinite integrals are? It would be the exactly same representation over here except without the limits. You know, as I said in the previous video, when you're looking at the differences between these two, the difference is you have an interval here, you don't have an interval. And the other difference is what the result is. The result of a definite integral operation is that you get a numerical value. The result of this, you get some sort of function with a constant. Those were the two prime differences between a definite and an indefinite integral. Anyhow, if you have a function that's continuous, you see this is a function which is continuous, there's no break in it, and it has an interval from a to b, then you can write the function in terms of this. If supposedly this sign capital Fx represents the integral of this function that you're doing the integration of this function f of x dx, your function is f right here. This right here is your function. This capital F of x represents here the integration of that function right over here. If you have a continuous interval over here from a to b, according to the fundamental theorem of calculus, at any point on this curve between the interval a to b, you can calculate a derivative of this function as well. So at any point between a and b, there's a derivative of this function, and you can represent that derivative as this. You see right here, this symbol here with the prime, that's a derivative. That's a derivative of this. You're doing a derivative of this, and you can represent it in terms of notation. You're doing the derivative of your integral. Look over here what I'm doing. F of x dx. Now basically what I'm saying, if you have a function and you take its integral, when you take an integral of your function, you've determined the antiderivative. That result which you obtain from an integration is called the antiderivative, especially when you're talking about indefinite integrals, because if you were to actually do the integration over here with the defined limits, you'd get a numerical answer. But if you were to do the integration of a function, you'd get another function with a constant. That result you would get from the integration of your function is called an antiderivative. I'll just write it over here as a antiderivative. So on a continuous function with a specified interval, you can do an integration of that function and you can get an antiderivative, and at any point on this curve you can take a derivative and get back to, now here's the main part of this theorem, you can take a derivative at any point of your antiderivative and you can end up coming back to your original function. If you haven't picked up on that, think about it as how I said in the very first part of this video, that they are inverses. Each one will undo what the other does. If you're taking your function and you're doing its integration and coming up with an antiderivative, if you take the antiderivative and you take a derivative of this antiderivative, like you're doing a derivative of it, you'll end up back to your original function. That right there is the crux of this entire fundamental theorem of calculus, where each of these two processes of derivatives and integration are inverse of the other. If you do one, you can undo it by doing the other. So the derivative of the integral is always gonna lead you to the original function. Now let me show you this in a perhaps less complex manner in the next part of this video. So with regards to this fundamental theorem of calculus, where I've said that both the process of derivatives and integrals are inverse of one another, I have said this. If you basically take a function and you do its integration, now I'm not presenting this in the format that books would present it. I'm going to use my layman form of showing you how. If you take a function and you take its derivative, you end up with basically, let's just say a capital F of x, and we'll call this the antiderivative. The antiderivative. If you take this antiderivative and now you take its derivative, you'll end up back to the original function which you started with. And that right there is a loop, where both of these functions are the opposite sides of the same coin. And you can represent the derivative of this right here also like this, with this prime. You're doing the derivative of this function and you're coming up with this prime. Anyhow, you're going to end up with the original function as a result of that. So the derivative of the integral is always going to lead you to the original form. Let me show you very quickly with a very easy example. If I have a function and the function is, let's say, 2x squared, I'll take the integral of 2x squared. You don't have to do integral first and derivative second. You can do derivative first and integral second, and I'm going to show you that. Let's take 2x squared and we'll do the integration of this. If you do the integration of this, you get 2x cubed over 3. That represents your antiderivative. Now if you take the derivative of this, and you know you have to use a power rule, 3 will multiply with that, and you'll divide it and you'll lessen that exponent by 1. Look what you'll get. 3 times 2 is a 6, x squared over 3, and you simplify that, get 2x squared. You see how we ended up with exactly 2x squared. If our original function was this 2x squared right over here, we took the integral of it, we got the antiderivative, we did the derivative of the antiderivative, and we got back to the original function. Now let me show you this. If I have a function, let's call that 2x squared, and let's take the derivative of this. When we take the derivative of this, what are we going to get? We're going to get a 4x, right? We're getting a 4x because you multiply 2 with 2, you remember the power rule, and you subtract 1 from the exponent. 2 times 2 is a 4, and you get x to the power of 1. Now let's do the integral of this. The integral of this, when you learn how to do it, and we're talking about here an indefinite integral because there's no interval over here, you'll get this play out. It'll play out like this. You'll get 4x squared over 2 plus c, the constant of integration. When you simplify 4x squared over 2, what do you get? 4 divided by 2, and you get 2x squared. And we can worry about the c later on because there's no interval, we have a c. But look where this right here and this right here match. You can now see clearly that the effect of one is negated by the other, or the effect of the other is negated by the first effect. Alright, integral, derivative, integral. They both undo each other and you eventually end up back at the original function. That right there in the most simplest form is a crux of the fundamental theorem of calculus. And you can see it right here in a very layman's form presented to you right here. And the beauty of this fundamental theorem of calculus is most well seen using indefinite integrals, because the result of an indefinite integral is a function and that function is an antiderivative. You can take the derivative of the antiderivative and end up back at the original function, because when you're dealing with definite integrals, your result will be a numerical value, not a function. So you can see all of that laid out to you over here. I want to show you some more of these inverse effects using some other types of functions, and we can appreciate this theorem some more. Take a look over here. If your original function is sine x, and you're asked to take the integral of a sine x, and you know you're going to end up getting an antiderivative. If you knew the rules of these type of functions, how you integrate them, and you did it, you would get a minus cosine x. That's what you would end up getting, minus cosine x but plus c, the constant of integration. Don't worry too much about this yet, because we have no definite integral. We end up with this for completeness sake. Now if you were to take the derivative of minus cosine x, you know you can write the minus out as a coefficient. You know the derivative of cosine x is always a minus sine x. You get a minus sine x, and you know you end up with the original function, which is right over here. So the integral of your original function led to an antiderivative. The derivative of the antiderivative led to your original function. So that you can see very well playing out in front of you. Let's look at another example. If we have another original function, and that function happens to be tan x. And now if you were to do the derivative of tan x, you know, based on the trigonometric function derivative videos, the derivative of this is going to be secant square x. Now if you were to take the integral of this, because we're trying to show how one undoes the other or undoes the other, if you were to do the secant square x, you would know soon enough that when we do the videos on integrals of trigonometric functions, you're going to get a tan x. You'll get it, and you'll end up back with your original function. Alright, and you're seeing that clearly over here. It's easy to appreciate how one undoes the other. It just is an inverse process over there. How about this? If an original function is 2x plus e to the x, let's do the integral of this. If you were to do the integral of this, you would get 2x plus e to the x. If you do the integral, you would get this. 2x will become 2x squared over 2, which will become x squared plus e to the x plus c, the constant of integration. This right here would represent your antiderivative. If you were to do the derivation of this antiderivative, if you do the derivative of this, you look over here, the power rule, 2 will come over here, and then the x exponent will decrease by 1. You'll get a 2x, and the derivative of e to the x, using the simple rule of the derivative of these exponential functions, is just going to be e to the x, and you'll end up with exactly what you started with. So you can see clearly over here, each effect is undone by the other side of the coin, with one side of the coin representing your differential calculus and your other side of the coin representing your integral calculus. So that's the beauty of the fundamental theorem of calculus. You can always arrive back at the original function by undoing one of the procedures that you have done, and that tells you how both of these procedures, the derivatives and the integrals, are intimately related but in an inverse manner. So this is not going to be a long video by any means, because we're just talking about, in a very layman sense, in a sense that we can understand, the fundamental theorem of calculus, where we're talking about the interrelationship between the differential and the integral aspects of calculus. I want to end this video with this last exemplification. If we have an original function which looks like this, if we are to carry out the integral first, we can undo it by taking the derivative of the antiderivative and come back to our original function. And I know we don't know how to do many of these integral processes, but that's fine, we will be learning them. If you take the integration of this, an indefinite integral, we would be using something over here which is called a substitution rule. You don't have to worry about that right now. U is equal to 2x plus 1, then du is equal to 2 dx, and dx is equal to du over 2. You would use something by means of substitution, and you would end up with this. You'd get root u and then du over 2. This over 2 can come outside as a coefficient, and you get root u du, which can be written as 1 over 2 integral of u to the 1 over 2 du. 1 over 2 du. If you were to actually finish this out now, you'd get 1 over 2 times u to the power of 3 over 2 over 3 over 2, and if you simplify this, you would get this. 3 over 2 would flip around, cancel out with the 2's, you'll get a 1 over 3 u to the power of 3 over 2, but what did u represent? It represented 2x plus 1 to the power of 3 over 2 plus c. That right there would be your antiderivative. If you were to take the derivative of this antiderivative, you'll end up with that. And I will show you that right here on the bottom. And here, you know we have a composite function, so you remember all of that. If u is equal to 2x plus 1, then f of u is equal to u to the power of 3 over 2. Remember the chain rule? Now we're talking about derivatives over here. So we have to do all of that. So you'd have 1 over 3, you can bring it right outside your derivatives. You don't need to even worry about the 1 over 3 because it's a coefficient. D over du, 1 over 3 times d over du, u to the power of 3 over 2, and then du over dx, 2x plus 1. Remember, we're doing the derivative here of this antiderivative. If you take the derivative of this antiderivative, you should end up back with the original function. Look over here. You have a 1 over 3. The derivative of u to the power of 3 over 2 is 3 over 2 comes out, 3 over 2, and then u is reduced to the power of 1 over 2. Remember, it's always a power rule. Exponent comes out as a coefficient and the exponent is reduced by 1. And the derivative of this is just a 2. Now we have nothing more than the simplification of these fractions. This 2 cancels out with this 2, this 3 cancels out with this 3. This was a 3 over 2 as you remember, and you just are left with u to the power of 1 over 2. But what did u to the power of 1 over 2 represent? 2x plus 1 to the power of 1 over 2. And this right here is our derivative. We've essentially done the derivative of the antiderivative and ended up back with our original function, which represented f of x. So I will show you. Remember, originally I was using those different type of symbols. This right here was my capital F of x, right here. My derivative over here. This right here is representing the derivative of my antiderivative. The derivative on the antiderivative is equal to your original function. That's perhaps the most important line of this fundamental theorem of calculus, which is really a part 2 of the fundamental theorem of calculus. But anyhow, one of the most important lines is that the derivative of your antiderivative, which is the same thing as saying the derivative of your integral, is equal to your original function. Finally, for this video, it bears repeating this. If you have your original function and you're going to do its integral, you do the integral and you come up with a result which we will just graphically show as this in representation form. This right here is your integral of your original function. It looks like a dollar sign, but it's an integral. And now you do the derivative of this antiderivative. This right here, if you're doing the derivative of your antiderivative, you're going to end up with this. The thing I'm saying is this original function will be the same as this. It'll be the exact same. The derivative of your integral will be the same as the original function. You can also look at it in the other way. If you have an original function and you take its derivative, right, you're ending up with something which looks like this, the derivative of your original function. Now if you take its integral over here, right, integral, you're going to end up with an antiderivative here. This antiderivative will be the same as your original function. So it works both ways, and it just doesn't work one way, but it works both ways, and I've shown you examples in this video of both. Each procedure, the integration or the derivation, will undo the effect of the other such that you'll end up back to where you started. You can do integration first, followed by derivation, and you can end up back to the original function. You can do the derivation first, followed by integration, and end up back to the original function. Why is any of this important? Because when you're doing these types of questions, you can test if your answer is right, especially when you're doing integrals. When you get to your final result for indefinite integrals, which are your antiderivatives, you take the derivative of the antiderivative and you end up back with your question, then you know your antiderivative is calculated correctly. You know that your resulting function is correct because it's a way of testing your work out. This right here, Fundamental Theorem of Calculus, is an excellent way of testing your work out and making sure your answers are right. I hope you enjoyed this video. Please stay tuned for calculation videos coming up next with regards to integrals. We'll start learning how to integrate the various functions in calculus. So stay tuned. Those videos are coming up. Have a nice day. Bye.